Okay, previously we discussed digital circuits and we left it here. Let's go through and continue our discussion, and we'll look at some different kinds of circuits. So sometimes when we're designing circuits, we'd be interested in starting with a truth table, which basically describes the functions. Here's the inputs A and B, here's the output C, and then the question is, what is the circuit for that? So what does that, how do we actually implement that? So let's take a look at this one. And there are many ways of doing it. There are formal ways of doing it. We're going to do it more ad hoc. So let's take a look at this. We know that there's only one of the four input patterns that produces a 1, and that's right here. Okay, this is the only input pattern that produces a 1. Everything else produces a 0. So what I'm kind of thinking about is this looks a little bit like an AND function, okay, in the sense that there's only one one input combination produces a 1, but it has a 0 for B, or B is 0. So let's go through and let's play a little trick here. Let's take our input B, okay, and instead of dealing with the input B, we're going to look at B bar, okay? So if we're going to look at not B, this would be a 1, this would be a 0, this would be a 1, and this would be a 0. Well, this is not properly ordered, but if we think about it a little bit, 0, 1 gives us a 0 and so on. This is actually an AND function. So here's what we can do. We can start off with our signals A and B, and we can invert the B signal. And so now we have this not B right over here. And that's what we have over here. Okay, and then we know in order from these two signals, all we do is put them through an AND function, and we will get the proper result, where this is A and not B, which is our desired C. So that's one way of doing it. Okay, it's just by inspection. You can do it easily that way, by looking for tricks about what functions appear here. Let's go through and let's see if we can find a truth table for this particular circuit. Oh wow, it looks pretty complicated, but the easy way of doing it is to just run these numbers through it. Okay, so we're going to apply a 0, 0 to it. Okay, and so what does that do? Okay, let's see. This is an OR function, so we have a 0 here and a 0 here. That means we have a 0 out here, and it means we have a 0 here. Okay, this is an AND here. We have a 0 here for the input. We have a 0 here for the input. We have a 0 for the output. And then this is an inverter, so we have a 1. Now we have a 1 sitting here. This is an AND function. This is a 0 and a 1 to the AND function. We get a 0 out here. So we get this entry in here. So let's go through and try and let's say another entry, and I'm going to see if we can confirm this one. So A is 1 and B is 0. So we do the same thing. 1, 1, 0, 0. So what's a 1 or 0? That's a 1. What's a 1 and 0? That's pretty easy. That's a 0. This becomes a 1 here. We have a 1 here and a 1 here. Two 1s, when we AND them together, give us a 1. So we have this. So the way that we could go through and evaluate a circuit is to go through an exhaustive inputs. In this case, that would be we did 2 possibilities. We'd have to do all 4 possibilities. Take my word for it. This thing looks like this. So this truth table is exactly this circuit. Okay, now this is kind of you say, why in the world would we want to do something like this? Well, it turns out this is actually something that's quite useful for a whole bunch of things. We'll find out it's useful for algebra or for arithmetic. So what we want to do is we want to say, well, this table, okay, what we just went through, which is here, is actually something that has its own symbol, and this is called an exclusive OR. Okay, so it's an exclusive OR, and it's abbreviated XOR, and it's shown here. It looks like an OR gate, but it has another little line back in here. Okay, so it's an OR gate with kind of a second line behind it, and it's shown as an OR with a circle around it. Okay, and this is the truth table that we just discovered. So actually, if you wanted to build that circuit, what you would probably do is you would just basically find an exclusive OR gate, and you would get that circuit in just one gate. Okay, let's take a look at somebody like this. Okay, so we have a circuit that has an A, it has two inputs, has one output, and what it does, it's an AND gate in cascade with an inverter. So what happens here? Well, this signal right here is just A and B. So what we would do is we would write this signal right up here, and this is just this part is just the truth table for an AND gate. Okay, and what does the inverter do? The inverter just flips everything over. So where we got a 1 here, where we got a 0 here, we got a 1 here, 0 goes to 1, 0 goes to 1, 1 goes to a 0. So what is the truth table for this? We would just leave this center table out, or the center column out, and the truth table would look like A and B and C. But we'd use this kind of intermediate result to help include this. Okay, well that actually turns out to be a useful function in itself. So there's a name and a symbol for this combination of an AND gate followed by an inverter, and this is called a NAND gate, N-A-N-D, okay, or not AND. Now the way that we show it is kind of interesting. Whenever we want to do a NOT, we just put a circle on the back end of an AND gate. So this is an AND gate with a circle. That's a NAND gate, that it has the output that looks like that, or the truth table looks like that. Now, there's all kinds of combinations. If we have an OR gate followed by an inverter, this thing is called a NOR, N-O-R, not OR, and the truth table looks something like this. Or does it look something like this? Yes, it does, because let's go through and look at it. At this intermediate stage, we have A or B. So we would take a look at this. A, when 0, 0, that would be A or B is equal to 0, and then that means that not 0 is 1. When we look at 0, 1, that would be A or B is equal to 1, and then not 1 is equal to 0, and so on. So yes, indeed, this is the truth table for a NOR gate. So we can be armed with all kinds of these gates. Okay, let me just do one more thing, and then we'll go on to an example. And this is a case where we have an OR with a little circle on one of the inputs. Whenever we see a little circle on an input, it actually does the same thing as a little circle on the output. In the sense, it's shorthand notation that there's an inverter here. Okay, so this circuit is identical to this circuit, just shorthand. Okay, and we could go through and do the truth table on this, and we do the truth table. It looks something like this. When A and B are applied, the thing that's actually applied to the OR gate, this point and this point, is actually instead of a 0, 0, it's a 1, 0. 1, 0 applied to an OR gate is a 1, and then so on. We can go through and get the table here. Generally, we would get rid of this intermediate column in the table, and this would be our truth table for that. So we're going through and building those. And then finally, let's look at the inversion of an OR function, okay, which is kind of cool, okay? So here's what I'm going to do. I'm going to take an OR function, okay, and I'm going to go through and I'm going to do this with it, okay? I'm going to invert the inputs and invert the outputs, okay? So see what happens here. Okay, if I invert the inputs and the outputs of this OR, I would end up with a 0, 0 here. When I invert both, it gets a 1, 1. I'm sorry, this is an OR and this is an AND. I wasn't paying attention. See what happens here? This has this nice smooth back end, and this has this front here. Okay, so what I'm doing is this is an OR function, and this is an AND function. But I've inverted both the inputs and the output. Okay, so thank goodness I had that correction. So if we invert the inputs, we would take the inputs A and B and we put them down here. This is the results after we invert them, and this would be the product of A of those that would be A and B, and this would be the because the fact that we have a circle here, this would be the NOT right here. Okay, so if we do it also when A and B are 1, we would have the inputs to the AND gate would be 1, 0, or 0, 1. A and B are 0, 1. Then we'd have the inputs to the AND gate to be 1, 0. The AND gate would give us a 0, which comes out to a 1, and then so on. Okay, so we can build this truth table to find out that we would have a situation that when on this circuit with these inputs we would derive that out those outputs. Okay, hold it. Take a look at this. This is what the OR truth table is. Compare that with this truth table. They're identical. Okay, so this allows us to use an AND gate. Okay, this is actually a NAND gate, N-A-N-D, to produce a OR function, okay, if we invert the inputs. And this is not a coincidence. This is a consequence of this whole area of Boolean algebra, which, by the way, we're not going to really touch on. It just wants you to be aware of it. And it's actually the part of it's called De Morgan's law. And so we can actually do a lot of fairly sophisticated algebra on these digital logic functions, and those are quite useful if we want to simplify things. Okay, let's do the final thing. We're going to add a couple of digital binary numbers. Okay, so a binary number is represented by 3 digits. Okay, or by digits, a ordered sequence of digits. So this would be 0. This would be the first digit, second digit, third, the last digit. Okay, and these this one would have a value. This digit indicates a value of 1. This digit indicates a value of 2, and this digit indicates a value of 4. So for example, suppose I want to add together 2 binary numbers. Okay, this binary number is actually equal to 1, and this binary number is actually equal to 4. Why? Because this number up here, the A number, has 1, 1, 0 2s, and 0 4s, so it's a 1. The B number has 0 1s, it has 0 2s, and it has 1 4. And so we do it that way. So just like we would be doing long addition, we do addition in binary, where 1 plus 0 is 1, 0 plus 0 is 0, and 0 plus 1 is 1. So this is actually, let's see what this is. This is 4, it is 0, and this is a 1. This thing is equal to 5. So we indeed know that 1 plus 4 is equal to 5 in decimal. So we can do stuff like that. Okay, we can make it a little bit more complicated if we want, because this is the case of what? This is equal to 1, and this is equal to 5 with our representation, binary representation. So what's 1 plus 1? Well, that's a 2. So what it is, it's a 0, and it's a carry the 2 which is we carry a 1 into here. That gives us the power of 2. It gives us the value of 2. What's 1 plus 0 plus 0? That would be 1. There's no carry in here, so we might as well show a carry of 0. And this is 1 plus, or 0 plus 1, and this would just give us a 1, 1, 0. So this is a 6. And yes, indeed, 1 plus 5 is equal to 6. And in our final example, with this to give you an idea how this arithmetic flows, is let's go through and do a lot of carries. So let's see, we have a 1 plus 1, that's a 0, and we carry a 1. Okay, this is 1 plus 1 plus 1, which is a 1, and we're going to carry a 1. And this is 1 plus 0 plus 1, which is a 0, and we're going to carry a 1. So in this case, when I add this A number, which has what, a value of 3, to the B number, which has a value of 4 plus 2 plus 1, which is 7, I'm going to get a number that has a value. Let's see. This is a 0. This is a plus 2. This is another 0, and this is a plus 8. This thing has a value of 10. Guess what? 3 plus 7 is equal to 10. Now, why are we doing this? Because I just want to show, we can use this as a way of designing a circuit, or use for a circuit. Okay, so we could build an adder that would do this. Okay, these are the inputs. Okay, shown as this is just a 3-bit adder, and these are the outputs. Notice it has to give a 4th bit for that overflow, the last one we did. Okay, so we could generate the truth table for it. This has 64 entries in the truth table. I gave you some of the entries that are just awful. Okay, and so there's no reason this would be a hard thing to build. But we can actually build it a little bit more cleverly if we're willing to do this. In this case, what we're going to do is we're going to build a little adder. Okay, and this is called a full adder. The full adder has 3 little full adders. So this is a full adder 0, this is full adder 1, and this is full adder 2. This is a little circuit. And what the circuit has a carry in, which is right here, and it has a carry out, which is right here, which is connected. The carry out is connected to the carry in of the next stage, and it's cascaded in the following way. And this carry out just goes right here to this output. And so what happens is if we can build something that takes the carry in, which is right here, it takes the 2 inputs and produces an output and the carry out, we can go through and cascade these to add any number of bits that we want, okay, by using this full adder. Well, so if we would take this thing apart and we'd show it here, is we can design each module. Designing each module looks something like this. This looks like this is the carry in from the previous stage. This is the carry out to the next stage. These are the 2 digits we're adding together in this stage, and this is the sum for this stage. So what we have here is we have 3 inputs, carry in, the A bit and the B bit. We have 2 outputs. We have the sum for this full adder and the carry out for that full adder. And go through and convince yourself that this truth table works. And so what happens here with this truth table is we end up with something that looks like this for the sum, which is just a big old exclusive OR. And we have the exclusive OR here. For this carry, we have this representation here. And that would be the thing that we're going to end up building in the lab. So we're going to actually build a full adder in the lab, and I'd like you to review this to come to school so you're ready to do so. That's the end of this particular video.